Hello everyone, today we will be making a multi-harmonizer using Grainflow. This won't be using a poly or anything, it'll be using a single Grainflow object and we'll be controlling linked tables in the Grainflow to allow us to set the parameters of certain grains directly. For this tutorial, you'll need, at the time of this recording, the newest version of Grainflow. Today's August 29th. After I record this, I'm going to get this new version uploaded to the package manager, and of course it will be on GitHub. In making this tutorial, I found some bugs in Grainflow, and well, I fixed them. So you'll need the newest version. First, I'd like to demonstrate what we are building with this Grainflow multi-harmonizer. I'm just going to turn this down a bit and turn it on. So we're going to be able to set a transposition of n number of grains up to 4. So if we just wanted it like the last tutorial with a single harmonizer, I can give it a single number. So let's say 5. So it will go and transpose that up 5 semitones. Or I can send it a list, 0, 1, 2, 3, 4. So this will give us a chromatic cluster here, as you can hear. Or we can just give it random transpositions using some sort of algorithm. All right, so let's get started. All right, the first thing we're going to do is I'm going to paste a snippet that I've just added to Grainflow called Basic Live. And that will create our basic Grainflow Live setup right here. That includes our clock or our grain phaser, our recorder, our Grainflow, and our buffer, and our stereo panner. But of course we need to rename all of these things. I'm going to call this GF Harm for Grainflow Harmonizer. I'm just going to copy this into all these, and I also want this to have 16 grains instead of 4. So yeah, now they all have the name of my buffer that I actually want to use, and the number of grains I want, which is 16. And 16 is for the number of harmonizing voices, which I want is 4. We're going to have 4 grains per harmonizing voice. The first thing we're going to do, though, is just build the basic harmonizer using buffers. So we can use the n grains message in Grainflow to set the number of grains. So I'm going to set this to n grains of 4. And I'm also going to set the window offset to 0.25. So that means every nth grain will be multiplied in moduloed to the window offset. So the first grain will be at 0, the second will be at 0.25, the third will be at 0.5, etc., until it wraps around at 4, and that will be 0 again. So if I send these messages, we'll have effectively a 4-voice granulator. I'm going to make a Grainflow waveform so we can just look at it. Connect that in over here. And we need a sound. We'll use Anton. Connect it to my recorder. And then we'll also need to bang the waveform object to display the waveform. That's just an optimization. So if you have a granulator with a fixed sound file, you're not constantly trying to redraw the waveform. Oh, and by the way, if you didn't know this, if you add the @active attribute to a metro or QMetro, it just starts at a certain state. So if you do @active1, it just starts us on, which can be kind of convenient. Let's look at DAC. Oh, we want a multi-channel DAC, and we'll do an easy DAC. So we can hear what we're doing, and hope for that. I need to upgrade that snippet. My bad. Because we want a multi-channel live game, not a single channel one. Single channel one makes no sense. And that'll be fixed by the time I upload this. So start it up. And we have our beautiful Anton playing in our basic live granulator. All right, so in the other granulator tutorial, we used the rate message to control the rate of playback for the granulator. So if I do -5, it's going to play 5 times faster backwards. So let's do that. Oh, sorry, I connected that to the stereo pan. It needs to be connected to Grainflow. But yeah, doing that backwards maybe isn't the best idea, but you can see it is playing it a lot faster. The issue is if we do it forwards, and this is 5 octaves, so it's going to sound distorted, is it's going to go past the playhead, which we'll talk about changing the time when using the buffers again. So as you can see, when it goes past, it will play it again. Yeah. So if we do like something more reasonable, like 0.9. Oops. Yeah, you can see it's well, it's slowing it down, but we're getting some phasing distortion. So we'll also need a delay random, just give it some small amount, and this will just get rid of all the phasing. There we go. And at a rate of 1, there we go, the normal. So instead of using these messages like that, actually we should keep this delay random. I'm actually going to put it into this message box here that we'll use to initialize it. We're going to use different modes for rate and for the time. So we can use rate mode as a message we can send Grainflow, and it defaults to 0, it just uses that message. But if we send it a 1, it will read rates from a defined buffer using the index of the grain. There's another rate mode, which is rate mode 2, and it will randomly access the buffer for each grain. But we want rate mode 1 because we want a controllable harmonizer. And then we'll also need a buffer that will contain our rates. And we'll call it Grainflow harm rates. And it will have a sample size of 16, which is 1 per grain. So, and we can set the buffer by sending the rates message. That will set the rates buffer. So we want gf harm rates. And now if I do this, it's just not going to play probably because the rates should be set all to 0, but it is still playing, which means I messed up. Oh, you know what? I did it again. I connected that to the stereo pan. It's apparently a constant vice of mine. I'm going to go ahead and just move these down a little so I don't do that again. Here we go. Now it should, yeah, see it's not playing basically because like we're getting a bunch of DC because it's holding on to the one sample that it's on. So it's not moving, but it's effectively not really playing. So we need to set all of the rates in this harmonizing buffer, or the rate buffer, to amounts that we can well use to change the harmonization of the grain. All right, so we need to set our harmonization rates in the buffer using the poke object. So I'm going to create a poke object with the argument gf harm rates. And this will allow us to set this gf harm rates buffer with the poke object. So I'm going to make a waveform so we can sort of see what's going on. Buffer name, gf harm rates. And I'm going to set in the inspector the vertical offset to 1 because we don't really care about much below 0 in this case. So just for example, this should set the first sample to some value. Maybe not. Maybe I need to tell it that first. Okay, 1. You can see it set that first sample to 1. If I give this a 1, it will set the second value to some amount, so 0.2, 0.5. You can see it does that as well. So we want to do these in chunks of 4, and that's because each grain, like voice, is 4 grains because we've chosen our window offset to be 0.25, so the overlap is 4. So we have a grain that then ends as a grain sort of like comes in, and 4 grains will be playing at most at one time, which gives us a pretty smooth harmonization. To do this, we can use an Uzi object with the arguments 0, 4, and 0. The 4 is the number of grains, you could say, that we're setting, and the 0 is the base. And buffers work in base 0, at least when you're using poke. So we have to send it as 0, 1, 2, and 3 to set the different values. And we'll just go ahead and connect this here. We're just going to set one voice for now. And then I'm going to make this a floating point object, which will allow us to save a floating point value and then send it into the poke. So I'm just going to clean this up a bit. There we go. And then we'll make a floating point box with a trigger bang float. So first we're going to send this to be stored in our floating point object, which is what that right inlet does. And then we're going to bang the Uzi to set all 4 of those first samples to 4. You can see it did it right there. Let's give it a test. You can see it's now playing. I'm going to go ahead and put this on loop. And let's do it at a rate of 1.2. And that's going over, so let's actually do it at lower, 0.9. There we go. So we also need to fix that problem where we're going over the right point, which is not ideal. Actually, another thing you can do so you can sort of see that is you can connect the record here, and we'll get this little bar that we can't really see unless I make the background color. So we can sort of see where the grains are relative to the right point. So to do that, we're going to need to make another buffer, which is going to be not GF harm rates, but GF harm trav. And so I've been using delay as sort of an alias for this trav parameter because it's easier to just get, but it's the same thing. You can actually, in the newest version of Grainflow, which you'll need for this tutorial anyway, use the delay mode and delays identifiers. It's fine as well, but I'm just going to use trav to keep it consistent with my example. So, and that stands for traversal, and that's just the point in the buffer that it's at, basically. So with that, we'll use trav mode, and we'll set that to 1, and trav offsets is going to be, well, the buffer we have there, GF harm trav. And we'll go and connect that to Grainflow, not StereoPan, as well. And then we'll need a similar sort of structure for this. Actually, we can just use the thing that's coming out of the floating point box to figure this out. But I guess the first thing we need is we need a way to set our grain size so we're actually aware of what it is. So I'm going to make a floating point box. And I'm going to label it grain size. Spell it right. And I'm going to make a send gf harm grain size. And connect that here. We'll go and convert that into a frequency. So the first thing we'll do, because this is going to be in milliseconds, let me specify that, is we're going to divide by 1,000. This will convert milliseconds into seconds. And then we will take the inverse, which will convert seconds into events per second, or hertz, which is frequency. So connect that all together and clean it up. And now we can set our size of our grain this way. So that's really small, obviously. Oh, yeah, it's because our trav was 0. Because when I copied the buffer, it replaced it all. So I just set that again, and so we're good. We can change our grain size now. You can see those are much smaller grains. You can kind of hear them because they're in the frequency area. So let's do something like 125, where we can't quite hear the grains, but they're still small. So if you remember from the last tutorial, to figure out where the grains are going to end up, all we have to do is multiply the grain size by the rate. So we'll use the rate that's coming out down here because it will match up with this Uzi. Let's make that look a little nicer. There we go. And then multiply. I'll be multiplying by that float. And I'm also going to do a trigger bang float here whenever we change the grain size. We're going to we'll do this once we add in more grains. We'll keep it like this for now. But we will want to set it up so when we change the grain size, it will update. So we'll set our grain size there. And we will not quite connect that because what we want is not where the grain is going to end, but we want the difference between where the grain would originally end. And we're going to subtract to figure that out. Actually, we want inverse subtraction. So I'll just put a box here so we can see it. I'm going to set this to 1.5 again. So it's to 1, which should be 0. If I set this to 1.1, we get a negative number, which means we've gone beyond where we want to be. So we'll need to update our position. And the reason I do this inverse subtraction is because I want this negative number, because how the trav buffer understands things is like it's in reverse to how the message is set up. And that is so if you wanted to set a granular texture just by setting points offset from the traversal, you can do that. Like in a more intuitive way. That's just a decision I made, doesn't make it right or wrong. But we only want to send this number in there if it is in fact negative. If it's not negative, we just want to set it to 0. So we could use a clip or something to do that with a just unreasonably large number at the end, or we could use an if statement, and I prefer the if statement just because it's a little more elegant and it will work in any situation. So I'm going to say if f1, which is going to be our input number, is less than 0, then f1 else 0. Just saying if the number is less than 0, output the number. If it's greater than or equal to 0, so not less than 0, output 0. So let's put another message box here so we can see it. And I'll set this to 1.1 again. You can see that goes through. And I'll set this to negative 0.9. And you can see it's set to 0 because it's above that number. So now we can turn this on. And if I set this to 1.1, you can see we're not getting all those errors from before. We can do something more extreme like 2. As we're getting some distortion because it's extreme, we're still not crossing the right point, which is good. That's what we want. So the next step is to get this set up to work with more than just the 4 grains that we have. So we want to be able to do up to 4 voices, so 16 grains. And this is scalable, so you could do more than that, as long as you increase the size of the buffers in the granulator. So let's set up another Uzi with 4. And we're going to have this set randomly, our transpositions. So I'm going to do random, let's do random 24, and then we'll subtract 12. So this will go up or down an octave, is what we're generating. We're generating a list of numbers between negative 12 and positive 12. I actually think I need to make the random 25 to do that because we have a 0 in there. Pesky little 0. So we'll do a ZL group, which will L.group, which will allow us to store the numbers together. Using the middle outlet of Uzi, we can output the whole list from the ZL group. So put the message box here. I'm going to bang up here or to the side. We'll clean this up in a bit. You can see we have a random assortment of numbers between negative 12 and 12. It actually might be better to use earn here because then we won't get any repeats. So we'll add a little trigger bang clear. I think that's what you send to earn. Let's check. Yeah. So we want to clear earn's memory before we activate it again. Or you don't have to either. You could. It could be interesting to keep changing the transpositions and never have them repeat. But now you can see we get all different transpositions, which is great. All right, so now that we have our group or list of transpositions, we need to iterate through them. And we'll do that using list funnel. List funnel is convenient because it gives us the index. Give it offset of 0, so it will start at 0 and then go up. It gives us the index, though, along with the value. So I'm going to use an unjoin here. And then we're also going to need a swap. And this swap is going to change the order of how these go through, because what would happen originally is we would immediately send our floating point and activate this without, we're going to need to adjust the output here by adding an integer. So for the first voice, we didn't have to do this because we were 0 through 3 was great. That's what we wanted. But for the next one, we're going to want 4 through 7. So for each index of our harmonization voice, we need to multiply it by 4 and add it to the amount. So the first one will be 0, 1, 2, 3. Then the next one will be 4, 5, 6, 7, and so on and so forth. So I got that. Oh, and another thing we'll need to do is convert semitones to rate, which we can just use this expr function. This is essentially just how you get equal temperament. So this will convert semitones to rate. You don't really need to understand it, just know that it does that. So if I did everything right, this should work. Bang. Yeah, you can see we have groups of 4, and they're changing their rates. Let's see what it sounds like. Oh, and we're only getting one voice right now because our end grains is always being set to 4. We now want our end grains to be set to 16. We want all of them to play. And in the example that will be in the Grainflow package, it's all it's dynamic, so you can look at that. So let's listen to it again. Oh, I connected to stereo pan again. My curse. There we go. So now you can hear that we have 4 different voices. So you can hear the multi-harmonizer is doing the multi-harmonizations, which is exactly what we want. So let's do some little quality of life things. Like, so whenever we change our grain size, we would like it to recalculate everything. So I'm going to put it in a ZL reg here. And whenever the GF grain harm size is changed, so our grain size, we're going to just trigger bang, and it will recalculate all of this stuff. Let's just make sure that works. It's not quite working, and I'm guessing we have an order of operations issue. So let's do this with a trigger. We'll do that with a trigger float bang, just to make sure these things happen in the correct order. All right, set it to 500 again. Let's just make sure we have something in the register. That could have also been the problem. So now I can change this, and it will update as well. So if you want something that sounds more cohesive, a smaller grain size with higher transpositions is going to be better. I mean, if you want that smeary sort of effect, you can go for a really big, like 1 second grain size. And you can get that way. Which can be cool in its own right. Maybe not quite a harmonization, but a cool effect. So yeah, I think that is all for this tutorial. Thanks for watching. and I hope I will get out the next one in a more timely fashion. See you next time.